What specific problem does the R0 framework aim to solve in the context of self-evolving LLMs, and what limitations of existing approaches does it address?
The R0 framework aims to solve the problem of training self-evolving large language models, LLMs, without relying on external human-curated data, which is costly and difficult to scale. Existing approaches, such as label-free reinforcement learning and self-challenging methods, still depend on pre-existing task corpora or external verification mechanisms, limiting their scalability and effectiveness in open-ended reasoning domains. R0 introduces a co-evolutionary process between a challenger and a solver, where the challenger generates increasingly difficult tasks based on the solver's capabilities, allowing for a fully automated and self-supervised training cycle. This framework eliminates the need for explicit supervision and external verification, addressing the fundamental bottleneck in advancing AI systems toward superintelligence. Additionally, R0's iterative process enhances the reasoning abilities of LLMs, demonstrating significant performance improvements across various benchmarks without human intervention.
How does the R0 framework work? Illustrate the process step by step, emphasizing the roles of the challenger and solver and the mechanisms of group relative policy optimization, GRPO.
The R0 framework operates through an iterative co-evolutionary process involving two roles, the challenger and the solver, both initialized from the same base LLM. First, the challenger is trained using group relative policy optimization, GRPO, to generate challenging questions that are difficult for the solver to answer. The reward for the challenger is based on the uncertainty of the solver's responses, incentivizing it to create questions that push the solver's capabilities. Next, the solver is fine-tuned on a curated dataset of these generated questions, where it receives binary rewards based on the correctness of its answers compared to pseudo-labels derived from majority voting among its own responses. This cycle repeats, with the challenger continuously generating more difficult questions and the solver improving its answering abilities, all without any human intervention.
Can you provide a simple yet illustrative example of how the challenger generates questions and how the solver responds to those questions within R0?
In the R0 framework, the challenger generates questions by utilizing the Group Relative Policy Optimization (GRPO) algorithm to create challenging mathematical problems. For instance, the challenger might produce a question like, "What is the integral of x squared?" After generating this question, the solver, which is trained to answer such queries, responds by generating multiple answers based on its current capabilities. It then determines the most frequent answer among its responses, which serves as a pseudo-label for the question. The solver's performance is evaluated based on how accurately it can match this pseudo-label, and it receives a binary reward depending on whether its answer is correct or not, thus facilitating its learning process through the iterative co-evolution with the challenger.
What are the theoretical or practical benefits of using the R0 method compared to traditional supervised learning approaches? Can you quantify any improvements mentioned in the paper?
The R0 method offers significant theoretical and practical benefits over traditional supervised learning approaches by enabling self-evolution without reliance on human annotated data. This framework allows for the generation of a challenging curriculum through the co-evolution of a challenger and a solver, which enhances the model's reasoning capabilities iteratively. Quantitatively, the Quen 3-4B base model demonstrated an average score increase of +649 points on math benchmarks after 3 iterations of self-evolution, while the Quen 3-8B base model improved from a baseline of 49.18 to 54.69, a gain of +5.51 points. Additionally, R0's training not only improves performance on specific tasks but also generalizes well, with average general domain scores increasing by +381 points for Quen 3-8B base, indicating that the method enhances underlying reasoning abilities across domains. This self-supervised approach thus amplifies performance beyond what traditional fine-tuning on labeled data can achieve, as evidenced by A+2. 35-point gain when R0 is combined with supervised fine-tuning.
How is the effectiveness of the R0 framework validated or tested? What datasets and metrics did the authors use to demonstrate its performance?
The effectiveness of the R0 framework is validated through comprehensive experiments on various benchmarks, specifically focusing on mathematical reasoning and general domain reasoning. For mathematical reasoning, the authors utilized 7 challenging benchmarks, including AMC, Minerva, and GSM-8K, employing GPT-4o as a programmatic judge to semantically verify the correctness of answers. In terms of metrics, they reported mean at 3.2 for the AMC and AMI benchmarks, and accuracy based on greedy decoding for other math tasks. For general domain reasoning, they evaluated the framework on benchmarks like MMLU Pro and SuperGPQA, measuring performance through exact match (M) accuracy. The results showed significant improvements across iterations, with notable gains in average scores for both mathematical and general reasoning tasks, confirming the model's enhanced capabilities through the R0 framework.
What limitations or potential drawbacks of the R0 framework are discussed in the paper, particularly regarding the quality of self-generated data and the challenges of increasing question difficulty?
The R0 framework faces notable limitations concerning the quality of self-generated data and the challenges associated with increasing question difficulty. As the challenger generates progressively more difficult questions, the accuracy of the pseudo-labels derived from the solver's majority vote declines, dropping from 79.0% to 63.0% by the third iteration. This indicates that while the questions become more challenging, the reliability of the solver's responses diminishes, potentially leading to ambiguous or ill-posed questions. Additionally, the framework's internal reward mechanism, designed to target a 50% success rate, may inadvertently result in a drop in data quality as the questions become harder, posing a critical trade-off that could hinder overall performance. Thus, while R0 effectively calibrates question difficulty to match the solver's evolving capabilities, the systematic decline in label accuracy presents a significant bottleneck for the framework's effectiveness.